Hello everyone, I am Yoona Kim from Seoul National University. I'm here to give a presentation of our paper entitled Integrated Host-SSD Mapping Table Management for Improving User Experience of Smartphones. So in smartphones, providing a high-quality user experience, UX in short, is known as the most important performance metric. To provide a high-quality UX, it is essential for the system to promptly react to a user input without a noticeable delay. For example, when a smartphone user launches an app, the system goes through multiple processes to get ready what a user requested. We call this time taken as the user-perceived latency. Every millisecond difference in the user-perceived latency has a high impact on deciding the UX quality. Then what decides the user-perceived latency? There are various contributors such as network IOs, processor computations, and storage IOs. And among these vectors, a long storage latency can significantly increase user-perceived latency while an app is being launched, switched, or loaded, where a massive amount of data has to be read from a storage device. Then what are the largest contributors that might cause a long storage latency? Among some other factors, we focus on the logical to physical L2P address translation in the storage system as one of the key contributors that could delay the storage latency. Because of a unique characteristic of NAND flash-based storage devices, for every request, the storage system always has to reference a corresponding L2P entry of the mapping table, which is stored in the flash memory. So for example, when the host system issues a read request with its host-managed logical address, the address translation layer has to translate the given logical address into a physical address, which represents the actual location of the data stored within the flash memory. So the address translation layer first checks the on-device SRAM memory whether the corresponding physical address is cached or not for a fast reference. If it is not found in the SRAM, the physical address has to be read from the comparatively slow flash memory. Then it can proceed the read operation of the data, and then the read data is delivered to the host. Therefore, the read latency varies depending on whether the SRAM held the corresponding physical address or not. With the SRAM cache hit, the read latency takes as much as a general flash read operation. However, with a cache miss, as an additional flash read operation to look up the corresponding physical address has to be issued, its latency becomes twice as longer. Therefore, here we address that an L2P cache miss as a key contributor for a long storage latency. Moreover, as the storage capacity of smartphones keeps increasing, the number of L2P cache misses also increases, which could further degrade the UX quality. This is because since the capacity of the storage device increases, the size of the L2P mapping table also increases proportionally, where its size is about 0.1% of the whole storage capacity. So for a terabyte storage device, its mapping table takes up about 1 gigabyte in size. However, unfortunately, the size of the SRAM is not as scaled as the storage capacity due to hardware and cost constraints of mobile systems. And in general, its size is about 512 kilobytes to 1 megabyte, even for a terabyte flash capacity. So as a consequence, there is a greater chance of L2P cache miss occurrences. Therefore, the user-perceived latency can be increased due to the increased number of L2P cache misses. So from our observation, in the worst case, the L2P cache miss took up about 33% of the entire user-perceived latency, which is quite significant. To overcome the performance degradation due to the limited SRAM, Host Performance Booster, HPB in short, was introduced, which expands the size of the L2P cache by borrowing the host-side DRAM memory. So here is an example of how HPB works. When the host system issues a read request, and if the corresponding L2P entry is cached into the HPB allocated memory, the host system can issue a read request not just with its logical address, but also with its physical address. Then the storage can directly access a delivered physical address by avoiding an expensive flash read operation. Therefore, read latency with an HPB hit is almost the same as the SRAM hit on the device side. So integrating HPB into the system can possibly provide better UX quality by reducing L2P cache miss penalty in the user-perceived latency. However, according to our analysis, we have figured out two technical shortcomings of the existing HPB in terms of providing better UX quality. This is because the existing HPB management scheme manages the HPB memory in a UX-oblivious storage-centric manner. The first issue we encountered was there still exists a significant amount of critical misses Here we define a term critical miss as an L2P cache miss from both HPB and the device-side SRAM, which results in an additional flash read operation to acquire the corresponding L2P entry. So whenever the host system issues a read request, it first looks up the HPB memory, whether the corresponding physical address is cached or not. Since the properties of UX critical app level information are not taken into consideration, most of the UX critical L2P entries might not be found in the HPB memory. So here an HPB miss happens. And if the device-side SRAM neither held the corresponding L2P entry, here a critical miss occurs. Therefore, the slow flash read operation to read an L2P entry has to be issued. So even under extended cache space with HPB, the critical miss penalty still exists in the user-perceived latency. Secondly, if HPB might improve the storage performance by reducing the number of critical misses, such benefit comes at the cost of reduced working memory space for user apps. Since HPB shares the host memory with the Android platform, the size of HPB should be carefully tuned. Otherwise, HPB may lead to killing additional user apps. So let's assume HPB was not integrated and the user wants to launch another app. In such a case, it seems to be no problem. However, if HPB is consuming the host memory, there is not enough room to load data for a new app, and the system suffers from memory pressure. In such a case, to make a room for a new app, the system chooses the least important app and kills it, which could possibly degrade the UX. Therefore, we address that we need a UX-centric HPB management policy to provide better UX quality in the HPB integrated system. To provide a high-quality user experience of the HPB-enabled system, here we introduce the design goal of our proposed work called HPBvalve. We propose two techniques that manage the HPB memory in a UX-centric manner. The design goal of our first technique, foreground app-centric HPB caching, goes as HPB memory should cache L2P entries of foreground apps over background apps to avoid critical misses of the user interacting foreground apps. And the design goal of our second technique, dynamic HPB size adjustment, is to avoid user apps suffering from the reduced working memory space. By applying these two techniques, we expect the system to provide better UX quality. I have introduced the background and motivation of our work, and from now, I will explain the results of the empirical study of the existing HPB management scheme. So we have measured and analyzed the user-perceived latency when HPB is integrated to the system. So this graph shows the app launching time of 3 different L2P cache settings of 3 popular smartphone apps. The red bar represents no HPB system that only caches L2P entries within a small-sized device-side SRAM. And the yellow bar, the baseline, represents the HPB integrated system. Lastly, the green bar represents an optimal case, saying that there is no critical miss penalty included in the user-perceived latency. So it represents an ideal case that we should aim for. From this result, we make 2 promising observation points. First, even though the HPB integrated system borrows relatively a large amount of memory that can cache about 25% of the entire L2P mapping table, it shows only a marginal improvement compared to the no HPB system. Secondly, the HPB integrated system even degrades performance when compared to no HPB system. With these results, we confirm that there exists a large room for improvement in the current HPB management scheme. So let me explain the root causes of the existing HPB management in more details. The first root cause we analyzed is about the app priority oblivious HPB caching policy, which results in priority inversion between foreground and background apps. To provide a high-quality UX, the user interacting foreground apps should always be treated in a higher priority than the user previously interacted background apps. However, the current HPB management setting only focuses on improving the storage performance, which counts the number of references and caches entries with high reference counts that are over its predefined caching threshold. So here, for example, it caches entries referenced more than 5 times. Since background apps have been used for a longer time than the newly launched foreground app, HPB caches less important entries associated with background apps. So HPB fails to cache useful L2P entries of foreground apps that have a high impact on deciding the user-perceived latency. As a result, HPB fails to cache UX critical L2P entries, foreground apps suffer high critical misses in the beginning of its execution. So this graph shows the number of critical misses over on foreground app's execution time. Not surprisingly, most of the critical misses are concentrated in the beginning of its execution, which could result in an increased user-perceived latency. So we proved that priority oblivious HPB caching policy is not beneficial in decreasing the user-perceived latency. The second root cause we analyzed is about memory pressure unaware size adjustment. Since host memory is still a valuable resource, the size of HPB memory should be carefully tuned. The existing HPB memory adjustment policy sets timeout timers for every cached entry, and whenever the track timer becomes 0, it evicts HPB cached entries to return HPB allocated host memory. Here, for example, the HPB manager evicts cached entries if it is not referenced for 20 seconds. So here's a simple example of how it works for 3 seconds. The system suffers from memory pressure at timeline 0. And to handle the memory pressure situation, Android system by default triggers low memory killer daemon, LMKD, to relieve memory pressure by killing the least important app. However, the HPB manager only decrements its track timers for the cached entries. So even if the system is suffering from memory pressure, the HPB manager does not evict any of its cached entries since none of the track timers became 0. At the next second, memory pressure still exists and LMKD again kills an app, while none of the HPB cached entries are evicted because its condition is still not satisfied. And at the last second, the system is no longer suffering from memory pressure, but the HPB manager finally gets to evict entries of A and E as they are not referenced for 20 seconds. And its eviction is not beneficial to the system, while it even sacrifices further cache hit ratios. Therefore, the HPB increased memory pressure causes unintentional app kills, which is not desirable for the system to provide high-quality UX. So we observed how the actual LMKD kill status changes due to HPB. This graph shows the histogram of LMKD kill counts of systems with HPB and without HPB. The Android system decides the priority level of an app based on its usage patterns, and LMKD utilizes such priority information upon its victim selection heuristic. So the higher the priority is, the more user perceptible the app is. As expected, when HPB is integrated, a greater number of apps and a higher proportion of high priority apps got killed by LMKD, where HPB led 180% more of the total number of app kills and specifically led to 50% more of high priority app kills. Such app kills could result in a longer user perceived latency for their future relaunches. So for now, I will start explaining about the design of our proposed work, which addresses the aforementioned limitations followed by the evaluation results. So we propose HPBvalve to overcome the limitations of the existing HPB management scheme to provide better UX quality. Here's the overall architecture of HPBvalve, which is composed of 5 key modules. HPBvalve prioritizes the foreground app in managing cached L2P entries in the HPB memory, and dynamically resizes the overall HPB memory size based on the memory pressure status. To this end, we implemented 2 monitoring modules in the Android platform, which collect the app-level information and the memory pressure status, and delivers the monitored information to the HPB manager, which is implemented in kernel. And based on the delivered information, 3 modules implemented in the device driver layer manage the HPB memory in a UX-centric manner. So the key idea of foreground app-centric HPB caching is to prefetch important L2P entries of user recently and mostly used foreground apps on their launches based on a profiled list. Here's a simple example of how we operate the foreground app-centric HPB caching. So whenever a user launches an app, the app detector is notified of a new foreground app launch, and it delivers a launch start signal to the foreground profiler. And the foreground profiler searches the profiled L2P list of the user-launched foreground app, and if the app is found in the profiled list, the foreground profiler requests the L2P manager to prefetch the L2P entries in the list. Then the L2P manager fetches the foreground profiler requested L2P entries from the storage to the HPB memory. So with this technique, the critical miss penalty of foreground apps, especially in the beginning of its execution, can be avoided. However, if the foreground app is not found in the profile list, the foreground profiler starts profiling its accessed L2P entries to prefetch on its further launches. However, since this benefit comes at the cost of reduced working memory, we propose a dynamic HPB size adjustment policy to appropriately decide the HPB size. So the key idea is to return HPB memory before a high-priority app gets killed by LMKD. So here is a simple walkthrough example of how it works. Whenever the system suffers from memory pressure, LMKD decides on a victim app to kill to relieve memory pressure. In such a case, the mem detector first pauses the app killing process and notifies the HPB regulator of the LMKD selected victim app. Then the HPB regulator decides how important the victim app is by checking the apps in the profile list. If the victim app exists in the list, it is regarded as an important app. In other words, a user recently used interactive app. To prevent the high-priority app being killed by LMKD, L2P manager preferentially reclaims the HPB memory by aggressively evicting low-priority entries to relieve memory pressure. So to evaluate the effectiveness of the proposed techniques, we implemented HPBvalve on the Snapdragon 888 mobile hardware development kit. The total DRAM size is 12 gigabytes, and the storage capacity was 1 terabyte, which requires 1 gigabyte for storing the entire L2P mapping table. As for the benchmarks, we evaluated 9 popular mobile apps listed in the table. So the first result is about how user-perceived latency is improved with HPBvalve. HPBvalve greatly decreases the app launching time and loading times for all apps. The average launching time is improved by 23% compared to the baseline. And the maximum app launching time improvement was observed with Uber, where we improve it by 43%. And the maximum loading time improvement was observed with Asphalt 9, where we improve it by 11%. So HPBvalve successfully achieves almost identical user-perceived latencies as the optimal for all apps. Secondly, to evaluate the impact of our proposed dynamic HPB size adjustment scheme on UX, we observed changes in the number of important apps killed by LMKD. This graph shows the number of killed apps in a log scale for each priority category. HPBvalve much lowers the total number of app kills by 25%. Since preventing high-priority app kills is mostly important with respect to UX quality, HPBvalve prevents about 70% of highest priority apps being killed by LMKD. This is possible because HPBvalve proactively prevents LMKD from killing high-priority apps by promptly returning the HPB allocated memory to user apps under the monitored memory pressure signals. So this graph illustrates changes in HPB memory size along with the reported memory pressure signals. And unsurprisingly, the baseline case allocates and frees HPB memory in a non-harmonized manner with the memory pressure status. When the memory pressure is present, it still allocates HPB memory, while HPBvalve promptly returns HPB allocated memory to relieve memory pressure. On the other hand, even under no memory pressure, baseline case decreases the HPB memory, losing its potential for further L2P cache hit ratios, while HPBvalve does not evict entries to maintain its potential to achieve high ratios. Therefore, HPBvalve successfully manages the HPB size in an harmonized manner with memory pressure status. So here's the conclusion of my talk. We have presented HPBvalve that efficiently manages L2P entries in HPB. HPBvalve works in a foreground app-aware fashion while considering the host memory pressure to avoid its negative impact on the overall system. As a result, we achieved near optimal user-perceived latency level for most of apps. For our future work, we plan to extend the HPBvalve to manage the device-side SRAM L2P cache as well. So thank you for listening to my presentation. Our source code is available at the GitHub address, and now I'm open to your questions.